Hi, welcome to our paper, Active Object Detection with Knowledge Aggregation and Distillation from Large Models, and we are from Peking University. Active Object Detection, abbreviated as AOD, the goal is to detect the bounding box of the active object, which is an undergoing state change. For example, carrot undergoing cutting, pot undergoing cleaning. Main challenges of AOD contain two sides. First, the large intraclass visual appearance variance for the same object under state changes. For example, in figure 1 carrot can be cutting using a knife, breaking by hands or making into juice. Diverse interactions with carrots leads to the carrots undergoing change with large intraclass visual variance. Second, the subtle visual changes between the instance undergoing state change or not. For example, in figure 2, there are multiple distracting no-change carrots highlighted by green boxes, and the active carrot with red box only has subtle visual deafference compared with no-change carrots. In practice, we notice that alterations in the object's state frequently stem from interactions carried out on the object. If we can establish well-informed priors that model this common-sense knowledge concerning plausible object interactions beforehand, we can uncover the aforementioned intraclass variance. Semantic interactions priors to capture multiple possibilities that may cause changes in object state. Visual priors to provide vivid images depicting state changes. Spatial priors to guide the model to distinguish where to pay more attention. Motivated by this, in this paper, we propose a new framework, namely Knowledge Aggregation and Distillation KAD. Firstly, we introduce a knowledge aggregator that incorporates threefold common sense pertaining to active objects, encompassing plausible semantic interactions, fine-grained visual and spatial priors, serving as a cheated teacher to facilitate more accurate AOD localization. Secondly, in practical scenarios, the category of active objects remains unknown during inference, rendering the acquisition of the aforementioned threefold priors challenging. To avoid the extra prior input at inference, we propose a teacher-student knowledge distillation strategy to transfer of knowledge from the cheated teacher to the student. Third, our proposed framework achieves state-of-the-art performance on 4 datasets. We construct a knowledge aggregator to collect triple complementary priors, semantic-aware, visual-assisted, and spatial-sensitive knowledge to enrich the detection process with pertinent priors linked to active objects. We establish the knowledge-enhanced detector as a teacher with the priors as oracle query, which is collected by knowledge aggregator to predict the active object. Due to the unknown active object in the input image during testing, it is also difficult to obtain the relevant prior knowledge. Thus, our model has a vision-based detector, a transformer-based detector, a student to detect active object without extra prior inputs. The student model will learn the knowledge from teacher via knowledge distillation, and only the student model will be used at inference. Knowledge aggregator includes 2 processes, generate and fuse. During generation, we will construct a prompt based on the input active object category carrot and input it into ChatGPT. GPT will return descriptions of possible interactions and possible tools when the corresponding carrot changes. Then we put these generated descriptions into the Stable Diffusion model to obtain. The image of carrot being cut with a knife depicts the state change of the object, which is fine-grained visual information. Next, we process the textual descriptions and image into vector representation using a multimodal model such as CLIP. The textual or visual represented by these vectors may be redundant, so we need to selectively aggregate the semantic and visual representations of the corresponding input. Thus, we use an attention layer and average cooling to fuse text or image vectors respectively. This query contains triple information, which can help the teacher model locate the active object more accurately. A teacher model leverages the priors to facilitate accurate representation learning. However, active object in the input image during testing is unknown, and it is also difficult to obtain the relevant prior knowledge. As a solution, we propose a distillation strategy that uses a plain detector as student using learnable queries to mimic the attention and intermediate outputs in a teacher detector using priors. The module contains 2 parts, 2 models parameters sharing and distillation on features and attention. Apart from distillation losses, the teacher and student will also optimize their predicted categories and bounding boxes using the detection loss function. Therefore, the loss function of the entire framework includes 3 parts: student model, teacher model, and distillation module. We evaluate our method on 4 AOD benchmarks: EGO 4D for daily activity, Epic Kitchens for activity in kitchens, Meccano for building a toy model of a motorbike, and 100 DOH a benchmark for hand-object interaction. Our method achieves SOTA performance on the 4 datasets. We conducted the ablation studies on the impact of different knowledge, and we find that each type of prior shows a performance gain, and combining the priors achieves the best results. We also explored different distillation methods, including distilling only features, or distilling features and attention at the same time. The experimental results show that distillation can foster the acquisition of detection capabilities by the student model from the teacher model, and comprehensive distillation strategies needs to not only align features but also bridge the gap between attentions. Finally, there is a visual comparison between our method and the previous SOTA method. The results of previous SOTA method are highlighted with yellow. Our results are red, and the green boxes are from ground truth. The incorporation of related priors to active objects in our method effectively guides the detection process towards active objects. In the attention map, Colors from blue to red means the weight of attention from less to more. The visualization of attention maps also proves that introducing prior knowledge of active objects can guide the model to infer and locate the active object by analyzing potential interactions. For a more detailed introduction, please refer to our paper, homepage and code. Thank you.